This PowerPoint, designed for the WE 101 course at Mohawk Valley Community College, deals with the atmosphere, origin, composition, and structure. Chapter 2 in your text. Of course, we're interested in the atmosphere because this is where the vast majority of weather takes place. The questions that are going to be discussed during this particular PowerPoint is the evolution of the atmosphere, investigation of some of the properties of the atmosphere, how meteorologists monitor the atmosphere, both surface and upper air observations, as well as remote sensing, the temperature profile of the atmosphere, and the electromagnetic characteristics of the atmosphere. As we will see, all weather is interconnected in some form. What happens in Africa or Asia or even Canada can have an effect on what goes on in the United States, as described in part by this slide. In discussing the evolution of the atmosphere, we have to understand the Earth system and what makes up the Earth system. As described here, the Earth system is made up of the atmosphere, the hydrosphere, the geosphere, and the biosphere: water, air, rocks, etc. The atmosphere, the one that we're most interested in at this point, is composed of a variety of different types of gases and suspended particles. Most of the mass of the atmosphere is found below 18,000 feet, with the vast majority, 99+%, found below the 20-mile range. Today's atmosphere is very different from the early atmosphere, or the atmosphere that we call the primeval atmosphere. When Earth was formed about 4.5 billion years ago till about 2.5 billion years ago, there were many different kinds of things that were going on. For instance, the sun was much fainter, that is, less heat. Carbon dioxide combined with rainwater to form something called carbonic acid, H2CO3. Oxygen was the most abundant gas in the atmosphere, the second most abundant, and nitrogen was the first. CO2, minor components of the atmosphere, have been around for about 3.5 billion years, but have fluctuated tremendously, as we will see. At about 2.5 billion years ago, carbon dioxide was low and oxygen was high, and there are still some fluctuations that affect change in the climate. For instance, we know that increased carbon dioxide is having a tremendous effect on global warming. During the modern phase of the evolution of the atmosphere, we appreciate that the lower atmosphere, 50 miles or so, circulates and maintains something called a homosphere, where gases are in uniform ratios throughout this area. Above the 50-mile range, gases separate based on weight, and this causes stratification and something we call the heterosphere. Today, our atmosphere, basically in terms of percentages, is primarily nitrogen, close to 80% or so, 78. Oxygen about 21%, with argon and carbon dioxide the next two prevalent gases, but in much smaller quantities. One of the primary differences between the heterosphere and homosphere is in its oxygen component. In the homosphere, it's in the diatomic form, and in the heterosphere, it exists in other forms, which we'll talk about a little bit later. Table 2.1 gives you the gas composition of dry air in the lower atmosphere, that is, again, below 80 kilometers or 50 miles or so, with nitrogen, oxygen, argon, and carbon dioxide being the most prevalent of the gases, as we can see from this. But notice all of the other components that are may be relatively small by volume, but still make up this thing we call our atmosphere. Hydrogen, krypton, methane, helium, etc. Although small in quantity, they are involved. Note also that water vapor varies greatly by location, and so it's not included in this particular table. Another component of the atmosphere are these things called particles or liquid components, which we term aerosols. Sources are from wind, erosion of soil, sprays, forest fires, industrial activities, etc. Water vapor by volume is less than 4% generally within the atmosphere, but it is extremely necessary for the formation of clouds and obviously precipitation. CO2 is essential for life, even though it's in relatively small quantities. Without it, we would have no process which we know as photosynthesis. Carbon dioxide and water vapor also have some very interesting effects because of their chemistry. They emit infrared radiation, which keeps the lower atmosphere warm and allows for life to exist. We can appreciate that the atmosphere has probably changed, as has our civilization and cultures. And one of the effects of that is this thing called air pollution. And this slide describes basically what is primary air pollutants and secondary air pollutants. And the next slide talks about some of the agencies involved with the monitoring the air pollution with standards and compliances, and I'll let you look those over. This next slide talks a little bit about the scientific method, which is important to us in this particular course, because the scientific method is how we utilize and basically come up with some very, very educated guesses about the atmosphere and some of the predictions that we make. We all know that some of those predictions at times are not as accurate as they should be, but that's the price of dealing with a very dynamic type of atmosphere. One of the things that makes our predicting possible is by using models, and obviously in the last 10 or 20 years or so we have come up with simulations because of computers that have given us some very, very important models to deal with. Conceptual models are basically a statement of a fundamental law or relationship. Example, the geostrophic wind model, which we'll talk about later. There are graphical models, which compiles and displays data in a format, for instance, a weather map. There are physical models, places where we can actually make weather occur, like a tornado vortex chamber. This vortex chamber, shown in the next slide at Purdue's tornado vortex chamber, simulates tornadoes and gives us some investigated analysis of how tornadoes actually form and work. One other type of model is something called a numerical model, and this is used by many meteorologists by way of mathematical equations to give us some input into an understanding of relationships among variables within the system. For instance, a global climate model and rising carbon dioxide are used and are considered scientific models. One of the things we have to appreciate is that models at times are not overtly accurate, and there are, because of missing and erroneous observations, accuracy at times can be a problem, as we all appreciate when watching the weather and seeing some of the mistakes that are made in those predictions. This next slide gives some historical perspectives on the atmosphere, and I'll let you look that over and kind of get a feeling as to when the earliest observations took place and how this particular process of increasing modeling as well as increasing the organizations that are taking over these modelings transpired. One of the interesting ones that you should probably keep in mind is that the Weather Bureau was organized as a National Weather Service in 1965 and was highly modernized in the 1990s, with today 123 or so modeling, or excuse me, National Weather Service offices throughout the country. Many of those are this thing called ASOS systems, which in our next slide gives you an example of what this ASOS, which is Automated Surface Observing Systems, are really all about. And this is a picture of one of them, and they are oftentimes found at our airports to basically feed information to an area surrounding that airport. It's a 24-hour-a-day feed, and there are, as you can see, a number of different types of collecting devices associated with this Automated Surface Observation System, or ASOS. Other ways that we could monitor the atmosphere is through the National Weather Service Cooperative Observer Network. These are stations that record daily precipitation, minimum, maximum temperatures, etc., that are used for hydrologic, agriculture, and climatic purposes. There are a number of these located in a region, and this information is also fed back to the National Weather Service for constant monitoring. Although lower air observations are good, upper air observations tend to be critical in terms of us making predictions. This slide with historical perspectives gives us an idea that some information was collected hundreds of years ago by using kites, balloons, and other operating upper air observations. The first more sophisticated type of observation in the upper air was back in the 1920s, when they used things called radio sondes. A radio sonde is nothing more than this. It's a balloon that's launched that carries a temperature sensor, GPS, pressure sensor, and it sends these informations back to the ground stations that release these, and they are released at a regular period each day, and the information that is gathered from them is then analyzed. Data from the radio sonde is monitored and actually converted into a graph or diagram called the Stuve diagram. And this looks complicated, but in reality these two black lines are the critical components of that, one being temperature, the other being the vapor content of the atmosphere, with wind direction, etc., being shown by the information that is received from the radio sonde balloon release. We'll learn more about this Stuve diagram in later chapters. You are all probably familiar with remote sensing by monitoring the atmosphere through things like radar and satellites. These remote sensing techniques are very, very critical to sending data to the National Weather Service and others, NOAA, etc. And these particular sensing devices are ones that we're going to spend some time talking about also. The atmosphere actually has a very, very interesting temperature profile, as shown in this next slide. You'll notice there are different layers of the atmosphere, starting with the troposphere, through the stratosphere, mesosphere, and thermosphere. The intermediate areas are called pauses: tropopause, stratopause, mesopause, which are the in-between areas of each of the other spheres. Altitude and temperatures are the x and y axis. You can see that there are some distinct differences in how temperatures are associated with each of these particular spheres. Notice there's a distinct drop in temperature during the troposphere, an increase in the stratosphere, a drop again in the mesosphere, and then an increase, tremendous increase, in what we call the thermosphere, thermo meaning temperature. The altitudes are associated with each of these again, and we will see why there is this tremendous fluctuation. This slide gives us some details about each of the layers of the Earth relative, or the atmosphere relative to its temperature profile. The one that we're really critically interested in is the troposphere, which is the lowest layer as shown. This is where weather, or the vast majority of weather, occurs. And we can see that, as shown by the previous slide, the temperature decreases with altitude. There is a distinct difference in thickness of the troposphere at the poles and at the equator. And as we said, the tropopause, as well as all of the other pauses, are transition layers, or transition zones to the layer above it. This next slide talks a little bit about the stratosphere, mesosphere, and thermosphere, and characteristics of each of those. I'm going to let you kind of look this over, but the next time you're taking a jet someplace, you'll probably be in the stratosphere, because this is an area of stable and ideal conditions for jet travel. This next slide talks a little bit about the ionosphere. And the ionosphere is really a component of partially the mesosphere and thermosphere, and is found anywhere from about 53 miles to close to 400 miles in altitude. And it's distinguished because it tends to be ionized by solar radiation. It plays a relatively important role in the atmospheric electricity that forms in the inner edge of an area called a magnetosphere. One of the things about the ionosphere is, as far as its practical importance, is that it influences radio propagation to a variety of distances. We notice that there are high concentrations of ions and electrons and electrically charged particles in this particular area. One of the things that is found as part of the ionosphere are things called auroras, which we'll talk about a little bit later, but these are generally visible only at higher altitudes, and we won't see many auroras here in central New York. In fact, this next slide shows us where the concentration of auroras are in terms of our location, and you can see from the activity that northern United States and most of Canada are not privy to many auroral phenomenon. Generally located in this particular area is where we would find most of the electrical activity associated with the aurora, and that's called the aurora oval. That's the end of this particular PowerPoint. There are a few slides in there I didn't talk about, so as you go through them, look those over, but I just didn't feel a need to talk about some of the things associated with that, although that does not mean they aren't important.